desired signal from the noise, maybe. And I want to use deep learning methods on this application, and my specific application is in telecommunication. First of all, let's go to what is a time series. What is time series? What does it mean? Yeah. Time series is a sequence of numerical data which is in successive order. It's do you have, because it was, I hope it. I'm sorry. Do you have my voice?
Yes.
Yes.
Oh, that's good. So it's a numerical data points, which is in successive order. It's the difference between time series and other type of numerical data, because they could be shuffled, but time series could not be shuffled. There are different examples of time series, like chaotic time series in telecommunication, radar, gravity waves, and earthquake. So these are some examples of our time series. And why we need deep learning methods. First of all, because some problems might just be non-convex and they have a high computational complexity. And sometimes we don't know the proper features about this time series. For example, you could see here a Lorentz system, which is a chaotic time series, and another one is it's just a received signal in telecommunication that you see. They are very complex, and when we want to optimize these signals, it would be very difficult. So one of the conventional methods in deep learning, is to map these time series into two-dimensional domain, and for example, using FFT or STFT or wavelets, or a space. It's like a space in time, and so this is frequency and time. These two are STFT, and this is in a space domain. So we could different first mapping methods, and then we could use the proper denoising deep learning methods, which it's an idea for me to use proper denoising deep learning methods on those two-dimensional time series in order to maybe reduce the noise. About the data set, there are available data sets for earthquake, and if you want to test the image denoising, and for telecommunication, could be measured, but it might be a little bit expensive, and there are not that much available data set for telecommunication signals, but we could generate it based on our models. And even for chaotic time series, we could, there are celebrated dynamical models that we could use. We could, in order to submit our report, we could use this journal, and there is a conference in Italy, which the paper submission for April 11. And these are my references. So if you want to discuss it more in detail, we could get into our slides.
Yes, I guess we have a question from Ahmed.
Yes, yes, Alizara, because thanks for the presentation. I'm also working on time series in finance, but I think I just did not get it. One of the points I did not get them clearly. Like, what do you mean by noise reduction? Because what I understand is like deep learning will be more used for making some kind of prediction. So,
oh yeah, you are you are working on time series forecasting, I think.
Yeah.
So I think in finance, the time series are noiseless because it just measures data. But let's see, we have time series in telecommunication that they're accompanied with error, because we have a measurement error or even the Gaussian noise that is just added to the desired signal. So we need to divide these two signals from each other. It's like a superposition of two signals. One of them is desired and the other one is not desired for us. It's the difference between the time series in telecommunication and finance, because your data all are noiseless. Maybe
kind of. We also have seasonal. It's also noisy. The financial data is noisy, but I guess your maybe data.
Yeah, you have.
But also we have a problem of seasonality and trend that we have to separate them.
I know these kind of trends, but they are not. It's like let's assume that someone is in finance. Even in finance, someone is. It's not the time labels or something is not correct. Maybe it's like it's not on the nature of the system. Every number you have is in the nature of your model, but sometimes our model have some error that we need to. Yeah.
Okay. Now I got the image. Thanks.
Yeah.
Thanks.
Okay. That's...
Any other questions? So Ali, if I ask you, what would be the title, for example, if you are writing a paper for this conference in April?
Maybe I was because my work in my project is in earlier stage, so I'm working on it. It's like a general topic for me. If I want to just work on this specific time without any application, it would be maybe time series noise reduction in telecommunication with application to telecommunication. But maybe it would be more specific if I could obtain more result from my other project that I'm working on.
So I mean, you need to, for example, to define some research questions which you want to answer, for example.
I will in the next maybe weeks working on them, and they are still in progress, but I will. Yeah.
Yes, and also need to read in literature, for example, what is there already.
This is my first idea, because I saw it from the other papers that they use the SDFD of the time series, and they use. But I want to know if we could use deep learning denoising methods on our time series. I'm searching for these kind of because usually these denoising methods are used for image, and I want to know if we could use it on our time series.
So this is very good. For example, some of those models which has been developed for images, we can transfer those models into time series.
That's my idea. Yeah.
Yes, so you can focus on this, for example. I mean, you need to check literature first if someone did that before, for example, if it has been done already, what has been done. I'm sure that people are working hard everywhere. So
maybe there are some work on this gravity waves because they are very noisy, and maybe in that area we could find some deep learning methods too. But in telecommunication, there are not. I couldn't find that much of these deep learning methods.
So in this case, if you are writing a report, you need to start by maybe writing, maybe introduction, title first, and in the abstract, I just need to define some research questions and define the method which we will use. And in the introduction part, you need to check what has been done already, the state of art in this direction.
I will.
So we don't repeat ourselves, right?
I do that. Yes.
Okay, thank you very much, Ali, for a nice presentation, nice project. And I guess, Irini, can you share your screen?
It should be Maria, I guess.
Maria. Okay, yeah. Sorry.
Or I think Irini already presented.
Okay, yes.
Okay.
Maria, so
Yes.
can you share your screen?
I think should work. Just a second.
Yes.
Can you see it?
Yes. Very
Okay. But for some reason it doesn't want to
You
make
can
it.
just make it full screen. Yes.
Yeah, I want to do that, but is it full screen now?
Full screen. Yeah.
Okay. Yeah. So hello everyone, officially like this. I will first tell a little bit about my background because when I chose the course, I was afraid that I don't have enough background to take it, since I'm coming from telecommunications background, and I'm actually doing a PhD at the Institute for Information Security and Communication Technology. The thing is that I had a switch in main supervision, so my main supervisor retired and I had to change. And the supervisor that I got assigned is dealing with machine learning. So I am a truly beginner in this area, but I think I can do it. So when it comes to research hypotheses and research questions, it was kind of hard for me to identify only one of these. So I had to put this one as a kind of umbrella research hypothesis that I'm currently trying to recon. So what we want to do is to design an autonomous, intelligent, and scalable 5G application of our interdomain network architecture. And we don't want to do this with application of machine learning. We want it to be autonomous and intelligent because in nowadays 5G networks are everywhere and there is tons of users, and the number of users and services and application is just increasing. And we are really not able to have a human interaction with the system anymore because that takes too long, and the latency for some applications, for example, intelligent car and whatsoever, is too big to have it. So we really have to have this intelligently and autonomously built in the system. And we want it to be application aware because there are different applications in 5G networks that have different requirements in terms of their latency and bandwidth. And we want this to be end-to-end. So we want really to know what is the latency for, or what is the bandwidth available for this and that service in every point of time. So basically, if I break this big research hypothesis into let's say one paper title, it would be 5G network slicing, like traffic isolation for QoE-aware network control. If I go term by term now, network slicing is isolation of specific networks flows where they are given certain bandwidth and latency delay guarantees. And then QoE aware means that every application, every service in 5G networks has different requirements, as I said before. So we really want the network to be aware of these requirements and to be able to, based on how strict or how not strict they are, do a kind of isolation in terms of network slicing so that each application gets enough resources that it needs in order for us to have happy users. So if I break the problems that we are working on now into two basic parts, the first one is to find the optimal number of different service classes, or basically network slices, and to cluster these milliards of flows in 5G networks based on their characteristics. And for that, we have this, we intend to use k-means clustering. And once we have that, we will use this. So for example, if you look at this figure on the left, we have many flows, and then we cluster them into, let's say, 5 different application classes. For example, file download, video on demand, SSH, voice or IP live video. And then we say that we have 5 application classes that have similar characteristics, similar requirements in terms of delay and bandwidth. And then we use these classes as an input to our second problem, which is basically how to allocate resources for all these flows in these 5 classes in such a way that all users are happy and it's optimal from the operator's perspective, in a sense that every flow, every client has enough resources, but we are not over provisioning, because over provisioning is costly for the operator. And that would look like the figure on the right, meaning that for the input, we want to use available bandwidth, number of clients in each of these application class, and then the application classes that we obtain from k-means clustering, minimum resource block size, that is basically a delta of how much bandwidth you can give to a different class, the minimum block size. And then we want to have alpha, which is a parameter for maximizing the QoE, because okay, there is a beta for maximum fairness between the applications. The thing is that if you maximize the quality for one service, then the other services will suffer. And what we want to do is to avoid that and kind of have this alpha and beta to control this optimization of the quality for some services, as well as the fairness between them. We cannot prioritize one specific service. All of them have to have kind of a fair share due to this network neutrality principle. And then we want to have this as an input to our neural network, deep neural network. And then the output will be the amount of resources that we assign to each of these 5 classes. The data that we will use, these inputs and the outputs, are all synthetic and obtained through simulations, and relatively easy to obtain as much as we need, because I have been designing the simulator for the past few years. So now that is in place, at least. And when it comes to the time plan, first we want to really decide on how this should work. And I think we are almost there, or actually what we want the machine learning to replace, because there are several heuristics that could solve this problem. But I think we already at this point I made this presentation 2 weeks ago, but I think we have this in place now. And then to prepare this training data set to see how to actually generate the data set from the simulator. And that should, at my estimation, should be 3 weeks, and then 2 months approximately to create and test the model and to write the paper. So the conference is in April, which is the target, but I am not sure if that is too optimistic or not. Let's see. Yeah, that would be it.
And I mean, this is very nice presentation, and I can understand the whole story from your few slides. So thank you very much for this clear way for I mean, communicating things. I mean, for this conference, do you need to submit the full paper, or it's abstract, or?
The abstract is in April.
Abstract in April, so you will have enough time to deliver the full.
I hope so.
Yeah. So this is, I mean, so chances will be much better in this case.
Yeah.
Yes, and the paper will be accepted based on the abstract.
Yeah.
Okay, so they will not check papers later on and reject.
No. I think the only the abstract submission is in April, but then I think it's 2 weeks, 3 weeks after that for the full paper submission.
Okay, so just maybe they need to use the abstract to be sure that it's within the scope of the conference.
Yes.
Yes, but I feel that this plan is very realistic, and you want to use some clustering algorithms. K-means clustering, it's easy. We need to cover it in the course here. And data set, you need to get the data set. How the data set look like?
Yeah, the data set I have to get, but the thing is that this first part with k-means clustering can be, how to say, avoided for now, and we can start from assuming that we have 5, for example, application classes. It's not that I need the first part in order to get the second one done, which is good. But the data set, I have already generated a table, so it's just to convert it to.
Yes, I mean the system in reality should be in real time. So you need to implement your system. It should be running in real time.
Yes.
To classify and the resource allocation, so people are happy. You need to measure this. Is there any way to measure this? How people are happy?
Yes, there is an optimization function that has a value for each configuration.
Okay, so there is objective function which you can give you an indication of. I guess this project is very, very good project. Very, very good work. Yes.
Thank you. I think the course is very useful because it looks like we will be able to design the model from scratch. So starting from, okay, this is the problem, how do I solve it? So that's why I think it really fits to the problem that I am starting to do.
I guess from now on, we will be working with those sklearn or other libraries, Keras, for example. It will make life much easier. So don't need, in fact, to implement things from scratch. We just need to know how to use those and the meaning behind it. So maybe the last
I meant more in terms of how to design this whole thing, like how to start with it, how to, I don't know, how to design, how many layers do I need, and these parameters that we are discussing, these kind of things. I think I don't have any experience from machine learning before, so for me it's very helpful.
Yeah, thank you very much. So any questions? Any questions to Maria? Any questions? Maria, your name is Maria, correct? Yes. Any questions to Maria? So so thank you very much, Maria. So just keep the hard work. So yes, we have Ola Magnus. Please, can you share your screen?
Yeah. Do you see it now?
Yes, we can see.
Yeah. Yeah. So my proposal is to experiment with transfer learning for weather removal models. Specifically single image weather removal, which means you have one image with bad weather and you want to get the same image without the bad weather in it. There's been quite a lot of work on such problems recently, especially with the automotive industry trying to get autonomous cars. But the models are typically complex and trained with huge amounts of data over a very long time. So trying to make something for another application than what they're trained for might be infeasible if you need to train it from scratch. So my research question is then, can pre-trained weather removal networks be efficiently transferred to both new background environments? So say going from cityscapes to more natural images, or for my case, in my PhD, to images taken in the Arctic, and can they be transferred to variations of the same kind of weather? For example, both light rain and very heavy rain and rain with a lot of wind, and also to other kinds of weather, such as rain to snow or perhaps rain to fog, etc. Yeah. So again, there are quite a lot of work on weather removal. So therefore, there are also quite a lot of synthetic data sets that have been used and have been published, which are free to use for training your own models. So we have, for example, Snow 100K, Raindrop, some unnamed data sets that have been used and published as well. So getting synthetic data isn't really a problem for this task. Real samples are a bit more difficult because, or it's more difficult to evaluate how the model performs in real samples, because you can't have the same image with both real rain and without rain, because that would be impossible to capture. But most of the datasets include some real images as well, to where you can test the model and see if it looks all right from a human's standpoint. Yeah, so my idea for the project, or the main motivating factor, is that all, or at least a lot of weather removal can be described as some way of separating the background image that you're interested in and a foreground weather layer. The definition of the foreground layer varies from different kinds of weather, but my hope is that a well-trained model has general enough of features that you can retrain it or transfer it to learn another representation of the foreground layer, and therefore, for example, remove snow instead of rain, or perhaps even be able to remove both snow and rain with the same network. So I'm interested in how well we can make a transfer model work compared to one trained specifically for the given task, because it's probably not likely that it will be as good, but if it's good enough, then perhaps this would be a feasible method to get this kind of functionality without training huge networks from scratch. So I'm planning to test different transfer learning methods, starting from simplest and then going more complex. So of course, the simplest is just retraining with new data and see if that works at all. Then perhaps switching out some parts of the network. For example, the last parts of the network are the typical ones. So you have the general features of the early layers, but then you learn new layers for the classification or the final parts of the networks. And then there are also more complex models or methods. For my master's, I worked with the domain adaptation using GANs, for example, which worked relatively well. So that might also be a possible way to go, although it's a bit more complex and difficult to train those models. But it would be interesting to see if that could work as well. Yeah, this time plan is really just a guess, but some weeks for literature review, and then after that, choosing models to work with to try to transfer based on both how well they work, but also how easy it is to get pre-trained models and tweaking those pre-trained models. Yeah. And then 1 week to actually get those models to work, because from experience, that isn't always straightforward, even though you can get pre-trained code or code with the models and pre-trained weights. And then basically the rest of the time available to experiment with transfer learning and writing up as we go along. Publication-wise, it could really be in any computer vision related conference or journal. So yeah, I just listed up the most common alternatives like CVPR, ICCV, ECCV, perhaps NIPS, although that's not that computer vision related. So I'd probably aim for CVPR, but all of these are really good conferences. So yeah, that was a bit quick, but I have another meeting at just a bit over 12, so I think I have to stop it there.
Yes. So thank you very much, Ola Magnus. Nice presentation, and it's very clear. In fact, research question is very well defined, and maybe starting with GAN neural network, it's good. Maybe could be good start point. Yes. So any question for other people, please? Yes. Maybe we have 1 minute for a question or something. No. Yes. Okay. So adversarial attacks or adversarial neural network, it's for maybe security part, or you have been working in your master thesis in adversarial?
Yeah, I've worked with a generative adversarial network to basically map a real image to look like a simulated image, and then we can train a reinforcement learning model in the simulation instead of using it in the real world, and then just transfer the images to using a real robot.
Yeah. Yeah. So I guess, I mean, this plan, it's hard work. I mean, your task, it's not easy. So I hope that by the end of the semester we will have maybe some good papers or some good reports. And we need to try different types of transfer learning models, stuff like this. So so thank you very much for your presentation, Ola.
Yeah.
Yeah. So I guess now we are at the end of today, and we will meet again next week. So next week we will try to finish this feed forward quickly, so we can start working with some deep learning models, and we need to work more with data sets and so on. So thank you very much for today, and please, if you have any questions during the week, just don't hesitate to send it to me by email, or just call me, for example. If you need us to discuss something more deeply, for example, we can just have a different meeting outside of the course, and we can discuss it by Zoom or by Skype. Yes, and thank you very much for today, and thank you for people who are presenting today. It was very nice presentations, and please keep the hard working, and thank you for today. Yeah.
Thank you.
I'll see you next week.
Thank you.
Thank
Bye-bye.
you. Bye.
Bye.